So welcome to the IAS Distinguished Lecture. So today we are glad to have Professor Younan Xia with us. He's a professor from Georgia Institute of Technology. So I believe that almost all of you know his name, right? He's one of the most important researchers in nanotechnologies. He got his bachelor degree in chemistry from University of Science and Technology of China back in 1987, and then moved to US to get his master's degree in chemistry from University of Pennsylvania in 1993, and then PhD in chemistry from University of Harvard in 1996 with Professor Georgia Whiteside. He then joined the University of Washington in Seattle as an assistant professor in 1997 and stayed there for 10 years. After that, he moved to another Washington University, the University of Washington at St. Louis, and stayed there for about 4 years. So in 2011, he moved to the current institute, Georgia Institute of Technology. Right now, he's a Brock Family Chair and a Georgia Institute Research Eminent Scholar in Nanomedicine. And here he uses all the joint appointment in different schools and departments. He is a fellow of American Chemical Society and American Institute for Medical and Biological Engineering and Materials Research Society. He is a highly cited researcher in both chemistry and material science. Right? And here's a number. He ranked number 5 in chemistry and number 4 in material science in the world based on the citation per paper. He currently published over 620 papers with more than 110 citations and a H index of 166. This is based on last year's number. I believe right now this number should be much higher now. Okay. So currently he's the associate editor of Nanoletters, and he has been in this position since 2002, and also a board members for near 20 journals. Right? So it's very active in the publications. So due to his great achievements in nanotechnologies, he has received many awards. Here I just list a few. For example, the Nano Today Award in 2013, the National Award in the Chemistry of Materials of SS also in 2013. So I don't want to read the non-list. Okay. So without further ado, let's welcome Professor Xia to give the lecture.
Okay, thanks for the nice introduction and invitation, of course. And also want to thank IAS for this opportunity to come here and share with you some of our research. And this is my third visit to this campus. First time was 2004. I spent 1 month in chemistry on my sabbatical leave. And then I came back, I believe was 2009, and this is my third trip. Every time you can see huge improvement, of course. It's always nice to see old friends, talk with them to know more about their everything. So in the first half of my presentation today, I'm going to tell you some fundamental studies about colloidal metal nanocrystal synthesis. And in the second half, I'm going to highlight some of their applications, some already in the commercial use, and some of them are still under development. And first, let me thank the funding agencies. That's always the most important thing if you want to do research. And someone has to give you the money and pay for everything, in addition to the students, of course. As Minghua mentioned, I'm a chemist by training. So I think, chemistry is really a good training. If you have a chemistry training, you can always move to any other different fields. For me, I have moved into biomedical engineering, for example. Not the other way around. If you start with BME as your major, you cannot do anything related to chemistry. It's always, when I talk to students, I always say I should probably start with chemistry. Okay, so that's a thing. So I have been doing research independently for about 20 years, actually exactly 20 years. So now we have about 3 major research thrusts in my group. And today I'm going to speak about 2 of them, about nanocrystal synthesis and also their application in catalysis. And we also have about 50% of efforts in nanomedicine and regenerative medicine. I won't be able to talk about it, but if I'm interested, we can speak afterwards. I sure have some time until tomorrow before I leave. Anyway, I'm sure everybody should have learned or heard about this. When you change the size of materials, you're supposed to see something new, all right? So here you can see easily, if you think about a gold, right? They have this beautiful golden yellow color. So now if you reduce their size down to the nanometer scale, okay, and their color will be very different. As you can see over here, this is a gold colloids suspended in water. They have this beautiful ruby red color. And that was basically, this sample is made by Michael Faraday in 1856. It's more than 150 years ago. And even before him, people already made use of this. And this is the so-called Nanocages cup that was actually manufactured in the 4th century. So in this case, people tried to make gold into very tiny pieces, below 100 nanometers. And again, to incorporate them into the glass wall, eventually this cup can display 2 different colors depending on how you shine light onto it. If you shine light from outside, you see this greenish color. If you shine light in the inside, you see this pinkish color. And those new colors can be explained using the phenomenon known as surface plasmon resonance. That's based on the interaction between the electromagnetic field of light and the conduction electrons in the nanoparticle. As we know, for metallic nanoparticles, they have very high density of free electrons or conduction electrons. And when they are hit by light, they are going to feel the electric field component of light. And of course, this light will change directions over time. So these electrons will be polarized along different directions. When the electric field goes up, and the electrons will be polarized down. And when switch direction, they're going to switch to other side. Okay, so basically, you can think about these electrons as like a collective oscillation, okay, over time. And this collective oscillation is known as surface plasmon resonance. Basically, give us 2 major phenomena. Okay, one is the so-called scattering. So the light can come in and scatter into all different directions and at same frequency or wavelengths. So that's the scattering. And in that case, you don't change the frequency or wavelengths of light. You just send them into all different directions. At the same time, this light could be absorbed and convert to something else. So that something else could be the vibration of the crystal lattice or heat. So in that case, you have this absorption. So depending on the size, shape, and composition and many different parameters, and this surface plasmon resonance can occur at different wavelengths or frequencies. And for gold sphere, about 40 nanometer in diameter, this resonant peak for gold is about like 520 nanometers. And absorption is in dominance for smaller particles, and in this case, it's about like 10 times stronger than the scattering component. But both of them are much stronger compared to molecular species, and this is a cross section, 10 to minus 15 square meters. For molecular species, even the best organic chromophores you can make is about like 1 million times weaker compared to this. So you can see the particle is very powerful in scatter and absorb light. And in addition to these 2 phenomena, you can also think about like other things like enhancement of local electric field. Okay, so anyway, for both this kind of optical light matter interactions, actually, you are going to observe like dependence on the shape of the particle. Okay, so here I want to use the silver system instead of gold to illustrate this because I have these calculations handy to show you. And for typically for spheres of this small size, you typically only observe one resonant peak. For silver, it's about like 400 nanometers. However, if you switch to particles with lower symmetry, like a cube, you are going to observe multiple peaks. And because the symmetry is reduced, you are going to have a number of different ways to polarize the electron. So that's why you can see the number of resonance is going to be different, of resonant modes is going to be different. And also, if you switch to like a gold, silver plates, and you can see significant shift of the resonance peak. In this case, about 400 nanometer, but here it's almost like 700 to 800 nanometers. And lateral dimension is about the same. It's about like 40 nanometers, but it's really the morphology or shape has been changed. And also, you can see the ratio of absorption to scattering. Okay, and for sphere, you still have quite some scattering component. But if you go to this thin plate, you don't have scattering anymore. It's essentially zero. The major component is going to be absorption. So you can see the dependence, okay, on the shape. And for field enhancement, here is very clear. You can see for sphere versus cube, at the corner sides, you can have much stronger enhancement in terms of electric field. This is about 4 times, this is about 30 times. So it's about almost 10 times difference. And if you put the molecules at these corner sides, their Raman scattering cross sections could be increased by almost like 10,000 times relative to this one, because it's proportional to the electric field raised to the power of 4. Anyway, yeah, the message I want to deliver over here is that we can control the shape of these kind of nanocrystals, and you can tune their optical properties, and you can also optimize their applications, their performance in some applications. But unfortunately, limited by time, I won't be able to show you some more examples. Okay, so I'm going to just use a few slides to deliver the message. So now let's come back to the synthesis, right? After all, whatever applications you want to pursue, you always have to start with synthesis. That's the very first step. And synthesis-wise, it turned out to be not so difficult, I have to say. Most people will be able to conduct in their own labs. And in this case, you only need to have, for example, a good system to control the temperature. And you can introduce precursor and the reducing agent, and then you will be able to make these nanocrystals. Unfortunately, if you look at the products, typically you are going to see the particles as shown over here. This is actually the case if you look at the old literature up till like year 2000. There might be thousands of publications of gold, silver, nanoparticle synthesis, but essentially all of them look like this. It's very poorly dispersed samples, and in fact, you won't be able to find any 2 particles that will share the same size or shape. It's very poorly dispersed. And those kind of particles could be used for some property studies or exploration of applications, but overall, it's not going to be optimized. It's not optimal for most of these applications or studies you want to do. And then, of course, that actually is taken from one of the early papers we published a long time ago. And we didn't stop at this stage as most people do. We start to ask ourselves questions why these particles are so non-uniform or poorly dispersed. So then we can find a solution. And it turned out to be related to a number of things, as shown over here. Basically, when you think about formation of these nanocrystals or nanoparticles, they always go through like 2 major steps. First step is nucleation, and then you have growth. For nucleation, they're going to just form seeds, and seeds will be further enlarged, eventually make this final larger nanocrystals. And for matters, as shown over here, those matters, they are phase standard cubic matters. They have tendency to form twin defects, because the energy needed or energy penalty for forming twin defects are so low for these systems. So that's why they always want to form twin defects. So as a result, during the nucleation stage, you may form single crystal seed. You may form singly twin seed, this red line over here indicates a twin plane in this crystal. Or they can form, just down a little bit. So maybe you can even have like more than one twin defects being incorporated in the system. And this is a structure with other types of defects like stacking faults instead of twin boundaries. And anyway, you can see the system is going to get more complicated. Okay, you are going to have at least these 4 different types of seeds being formed. And then from the same type of seed, when they grow in size, they also end up in different stages or different destinations. Like they can become cubes, they can become octahedral, tetrahedral, and so on and so forth. And some of them may take even elongated morphologies. So now you can easily understand why this sample look like this. Because if you don't really do good control, you are going to make a mixture of all these particles. So that's why it's so polydispersed. So now that's also very clear. If you want to make just one shape, you have to control the nucleation. You also have to control the growth. The growth typically is going to control by 2 parameters. One is the capping agent that can bind to a specific facet. Like 1O facet give us cube, and 111 facet will give us octahedron. So capping agent is very important. The other parameter is the kinetics. I'm going to show you some examples later. Okay, if the kinetic is not right, they may go to other shapes like this one. This particle and this particle are supposed to be similar in terms of surface structure. It's bound by 1O facet. They can be formed under capping of same capping agent. However, if the kinetics is not right, they may be elongated along one direction to form this bar-shaped nanocrystals instead of this perfect cubes. So you can see the kinetics is also very important. Anyhow, by controlling the nucleation and the growth, so eventually you can make just pure samples like cubes. And this is the rods sample. It's this one actually. There's some twin defect in it. And this is octahedron. And basically you can, this is a nanowires actually. It's one of these actually, making them longer where we give you these nanowires. So if you look at the literature now, actually now we can easily make this different shaped nanocrystals with reasonably good purity. Okay, so you can make almost close to like 100% purity nowadays. And it's also clear, okay, if you want to make the purest sample, you have to have good control over both nucleation and growth. And typically for nanoparticle synthesis, people like to use one-port approach. You have nucleation and growth basically in the same system. But unfortunately, that may not give you the best, the purest sample. Because as we know, the condition we need to make one particular type of seed could be very different from the condition you need for growth. So that's why one-pot growth in general is not the best approach to the pure samples. So that's why people start to look at like seeded growth. So in one step, we just make the seed, and then we have another step of growth, so you can have very good control in terms of shape. So let me show you just one example. In this case, we are making silver octahedral and the cubes by starting with a single crystal seed. We can make it. And then for growth, you just add more silver nitrate and ascorbic acid serve as reducing agent. And now you can play the trick of capping agent. In one synthesis, you can have sodium citrate. Sodium citrate actually will bind to silver 111 facet more strongly than 100. So that's why the final product is going to be enclosed in 111 facet. And in parallel, you can have a similar synthesis, almost identical except the capping agent. So you can use a PVP, polyvinyl pyridine actually. That will bind to 100 facet more strongly than 111. So the final product will be basically a cubic shape with 100 facet on the surface. So you can see this is a single crystal seed. You have to make sure they are single crystal by doing diffraction or maybe high-res TEM. And then you are going to make octahedral if you under this condition, under this capping agent. Or you can make a cubic shape if it's under PVP. So you can really see the correspondence. So you can really have almost 100% control. You can make this shape with almost 100% purity in this case. So yeah, so we have developed, of course, the capping agent or conditions for all these different shapes. If you're interested, you can look at the review articles shown over here. And during the growth process, it turned out to be also important for the kinetics, as I briefly mentioned. The kinetics could be understood in this way. Okay, you keep adding atoms to the surface. If the atoms cannot migrate to other areas, they might just pile up at the site of deposition. So eventually, we'll change the morphology of this product or the particle. So here's one example based on palladium cubic seed. Palladium cubic seed, you have this side face 100 surface that's capped by bromide ions. That's how we make them into cubic shape. Bromide is a selective capping agent for the 100 facet. But you have corner sides and edges not covered by the capping agent. So now when you add a more palladium precursor and the reducing agent, you are going to generate palladium atoms that will be deposited onto the corner sides first and then diffuse to other areas like edges and the side faces. So in this case, it turned out to be very important to consider the kinetics. If the deposition, you can imagine, okay, is so fast compared to diffusion, basically the atoms has no chance to diffuse to other areas before the next round of atoms come to the surface. So you can see the atoms will be piled up at the corner sides. So eventually the morphology of the final product will be octopods. At each corner you are going to have an arm or branch being formed. And then you can have condition with some increase of diffusion. So atoms can diffuse to the edges. So what you are making over here is going to be like a core frame structure. Okay, it's a core frame. You do have atoms deposited at the corner sides and the ridges or edges, and you're going to form a core frame structure. And then you further increase diffusion if you don't change the deposition rate. Basically, you're going to have more atoms going to edges at the same time, even to the side faces. And in this case, you're going to form a perfect core shell structure. So core shell structure will have same shape or morphology as the seed, just the dimension being slightly increased depending on how many layers of atoms you deposited over here. If the diffusion is too fast relative to deposition, the atoms will do reconstruction. They may change the shape to give something more closely related to thermodynamic favorable shapes, like octahedron in this particular case. Anyway, you can observe all of these different morphologies by basically controlling these two ratios. So in one experiment, we can fix the deposition rate. You control how fast the precursor is being added and reduced. That's the deposition rate. And then you can also change the diffusion by changing the temperature for the synthesis. So this is slow diffusion at the low temperature, and then high temperature, higher. So you can have faster diffusion. So basically you can observe this transition of morphology. For slowest diffusion, you're going to have octopods being formed. And this is going to be core frame structure, and this is a core shell structure, and this is going to be more close to like octahedron and so on and so forth. In another set of experiment, if you look at this paper, you can see that we can fix the diffusion rate. You use the same temperature, but you can change the deposition rate. You are going to observe essentially similar trend. Okay, if you have very high deposition rate, you're going to have octopods, and then that will basically change as the deposition rate becomes slower and slower. Okay, so it's basically it's a pretty unique control by controlling the kinetics. So let me just show you one example, two examples actually in more detail, the core frame and the core shell structures. So in this case, you can just have atoms being deposited at corner and edges, not the side faces. So eventually you form this so-called core frame structure. And the good thing about a core frame structure is that the core can be removed because the side face are not covered by the second matter. if they have different reactivity, you can selectively etch away this core. You're going to form this highly porous and open structure called nanoframes. And here just show you some different combinations of metals we have tested. The first metal is in the core. The second metal is at the frame side. So you can have palladium seed with rhodium grown on it, and palladium seed with platinum grown on it. And this could be even same metal like rhodium, platinum, rhodium, and so on and so forth. And for palladium rhodium system, actually, like this one, we can etch away the palladium very easily because rhodium is less reactive compared to palladium, so you can etch away. So eventually you can make these nanoframe structures. And those structures are pretty useful for catalysis because it's highly open. You have a high percentage of atoms being exposed on the surface. There are quite a large number of studies after we published how to make these nanoframes in year 2011 actually. And so now it's actually 2012 actually, yeah. So this becomes a very unique class of structures for catalysis in that case. And core shell is also important, okay, and let me show you some examples. Actually, they can become the focus for the last few slides in this talk. The idea over here is to do deposition like platinum on palladium nanocrystal seeds, so you can make a core shell structure. This is at different levels of magnification. And you can see the platinum could be uniformly coated as a conformal shell around the palladium. Okay, so you can control the thickness by controlling the ratio of platinum precursor relative to the palladium nanocrystals. And you can have 2 atomic layers being deposited, 4 atomic layers, there's 6 atomic layers, and so on and so forth. And you can also easily switch to different templates. You don't have to work with cube if you don't like. You can use octahedron. So for example, if you switch to octahedron, you can also make similar core shell structures. But in this case, the surface will be different. It's going to be 111 facet. As I'm going to show you later, this facet is better than 100 facet for oxygen reduction reaction actually, okay? So you can have a way to control the surface structure. And for atom diffusion, as we know, depending on the surface structure, they may have different diffusion barriers. So for cubic system, in general, you have to use very high temperature, almost like 230 degrees, in order to overcome the diffusion barrier to spread the atoms across the entire surface. And if you switch to octahedral templates, because the 111 facet is smoother compared to 100 facet. So that's why you are going to have a smaller barrier to the diffusion of atoms. And you can even lower temperature to like 90 degrees. You can also generate these core shell structures, but with much lower temperature. Okay, this is only for 111 facet. For 100, it's not enough. Okay, you won't be able to make these perfect core shell structures in that case. Anyway, yeah, so basically, yeah, by learning this kinetic effects, you can make some kind of interesting new structures for catalytic application. I'm going to show you later. But before I do that, I want to show you another thing that could be interesting to some of you. This is more related to like physics. This is like a symmetry breaking or reduction during the nanocrystal growth. And if you take a look at the seed on the surface, you always have so many equivalent sides related by symmetry, right? If you look at this square over here, this corner, this corner, this corner, these 4 corners are supposed to be equivalent to each other, okay? So now when they do growth, they have 2 major different patterns. One is like a symmetrical growth. You are going to have atoms being deposited onto all of these different corner sides. On the other hand, you may also have just the growth on 1 corner, or 2 corners, or 3 corners, like shown over here. And this one will have lower symmetry than this one, so that's why this is asymmetrical growth. Okay, and this actually could be manipulated if you control the experimental condition. Let me show you how we can do it. But before that, let me just give you some example that might be familiar to you, this kind of experience. So suppose you sit over here, this is a round table, and all of these glass walls are so symmetric to each other. So now if you sit over here, you see the symmetry is too high, will make you very confusing. Okay, you don't know. Oh, I should use left side, right side. You are going to debate basically. Okay, the symmetry is going to cause some trouble. However, the symmetry could be easily broken if someone carelessly pick up glasses from left side. The symmetry does not exist anymore. Okay, once the symmetry is broken, things will become much easier to follow. So everybody at the table will just pick glasses from left side. So the message I want to say over here is that symmetry could be easily broken randomly in general. And once symmetry is broken, and then in the next step, tend to just follow that particular pattern. So for nanocrystal growth is also the same thing. At the very early stage, when you add atoms to the surface, if the symmetry is broken, and then that symmetry will be maintained during the entire growth process. Okay. So now let's come back to take a look at the illustration I showed you earlier for nanocrystal growth. And in fact, we can single out those particles in the gray area. And these particles are supposed to be equivalent to these guys. The only difference is their symmetry are going to be much lower. For example, this tetrahedron. Tetrahedron is related to this octahedron because their surfaces are the same. They are 1, facet. However, symmetry-wise, this is lower than octahedra. So that's why you can imagine this is a product of asymmetric growth, and this is a product of symmetric growth in this case. So basically, we can start to achieve even a better understanding in why certain shapes are formed during the growth process. And there are many examples. Okay, symmetry breaking is one of the universal phenomena you can easily observe during nanocrystal growth, of course, in other systems too. And here, let me show you another example. This is for the nanowire growth or nanorod growth. And typically, like this nanowire shown over here with this particular cross-section, like a pentagonal cross-section, they are supposed to grow from the seed with the dodecahedron shape, okay? And in older days, we assume this growth will be initiated from both sides of this dodecahedron seed, and then will be pushed onto both sides. So that's why the seed eventually is going to be sitting in the middle. So you're going to have symmetric growth. It turns out to be not always the case, depending on the conditions you use for the growth. The symmetry could be broken. For example, this is something we published 2 years ago. If you took palladium dodecahedron seed, if you add this silver precursor and some reducing agent under the influence of this polymer can coordinate with silver ions and make the reduction slower. And then you can observe unsymmetrical growth. And basically, the growth will only be initiated from one of the two sides, not both sides, and eventually will push toward one direction. So that's why the silver will be deposited over here, and this end is still going to be covered by palladium. If you do elemental mapping, you're going to see it. Palladium is going to be located at one of the ends. So it's an unsymmetrical growth process. And here's something we published last year. This is for copper. It's a similar system. It's a palladium dodecahedral seed. You have copper being deposited. Again, it's only going to be along one side of this seed, not both sides. So that's why finally this palladium will be located at one of the ends. It's not in the middle. Okay, the symmetry is broken during the growth process. So why is that? Then we start to do some other demonstrations, figure out. Turn out to be related to the very beginning of the seeded growth. When we do seeded growth, we're typically using drop-wise addition of precursor because you don't want to have additional nucleation events. So you always add a droplet by droplet so you can keep the concentration of precursor in the system very low. So in this case, in the very early stage, if you only add one drop or two drops into your system, and these drops of precursor can only generate a certain number of atoms. And those atoms, when you compare to the number of seeds, including their equivalent sites, and they may not be able to cover all of the equivalent sites, and then symmetry is going to be broken, right? So I used this cartoon to show the idea. So for example, for this cubic seed, if you have growth going to be initiated on the side faces. We have 6 side faces, right? So now if you only generate like 3 atoms, and the growth, of course, cannot be initiated from all the 6 faces. It's just impossible, right? If you have 6 kids, you only have 3 candies. Only give candies to 3 of the kids, not all of them. Okay, that's just impossible. So in this case, maximally you can only have 3 of the side faces receive the atoms for the initial growth. So this is going to be the stage of symmetry breaking. Once the symmetry is broken, the growth will be continued along this pattern. They're not going to change actually, okay? And that's basically the idea about symmetry breaking. We can easily test this idea. You can add this precursor at a different rates, and this is a very slow rate. So that's why you only have enough atoms being added to one of the 6 phases in the early stage, and the growth will be continued, will be initiated from one surface and continued. Okay, they are not going to switch actually. You can have growth from 3 of them and 6 of them, or it's just how fast you add this precursor. And you can, this is for palladium seeds with silver being deposited. You can do mapping under TEM. So you can see this is have palladium over here at one of the ends, and you have silver being deposited. And in this case, palladium is going to be located at one of the corners. You are going to have silver at other 3 side faces. And in this case, it's a symmetrical growth. You have palladium in the middle actually. Okay. And this symmetry breaking also applies to other systems, not just say palladium and silver, these particular combinations. So for example, also apply to same matter, okay, like a silver grown on silver. Okay, so you take cubic seeds of silver, you add more silver onto it. Under certain conditions, like shown over here, you have slow injection of precursor, and the symmetry will be broken in such a way you only have growth along one of the side faces. So in this case, all of these other 5 directions not allowed. They are not going to have growth. You only have growth along one of the directions. So that's why eventually it will give you the elongated rod-shaped or bar-shaped nanocrystals. Or you can have growth on 3 of the 6 side faces. So final product is going to be something like this. We call this semi-truncated octahedron. You take an octahedron, you truncate off 3 of the corners. The other 3 left will basically give you this very special shape. And this shape, depending on how they oriented on the surface, it may give you a triangular projection under TEM. There's one over here. Or may give you something like we call the house projection. So that's other different orientations. Okay, so that's basically the structure, this piece over here. Or you may have growth from all 6 side faces. So eventually I'll give you octahedron. So that's basically this system. So you can see this is kind of like a universal phenomena. Okay, can occur for the growth of all different colloidal metal nanocrystals, not just the system I show you over here. So in the future, you should pay close attention to this. This in general is controlled by the kinetics. Okay, if you have very, very slow reduction, and then symmetry tend to be broken in such a pattern, okay, in the early stage. So that's basically the last slide for fundamental studies. Okay, I hope you have had enough about this kind of science. So now let me switch gears, talk about some applications. So first, let me show you one that's already been commercialized. This is based on the silver nanowires we published quite a long time ago, about 15 years ago. And in that case, we can make uniform silver nanowires with diameters about like 40 nanometers. Nowadays, of course, we can push them further down to like 20 or 15 nanometers with even small diameter in this case. And what's good about these silver nanowires? Well, when their diameter is so thin, basically they are going to have pretty high transmittance or transparency in the visible region. They don't absorb light or scatter light in this region significantly. So when you mix these silver nanowires with a polymer and spin coated onto or just coated onto another polymer substrate, you are going to make this substrate conductive, transparent, and flexible. So that's basically what we need for a number of applications. One of them is about touch screen displays. This is the commercial products coming from Cambridge. It's a company in the Bay Area. They licensed our technology. Actually, we didn't spend any time to commercialize these things. They did all this work, actually, okay? And now if you buy this tablet PCs from a number of companies, including like IBM, not IBM anymore, Lenovo, or maybe Acer, and all these companies. And basically, their screens is based on silver nanowires. It's not ITO or other materials. Okay, so they do have some applications already. And now they are also in the process to move into smartphones. So in the future, when you buy Samsung or iPhones or these smartphones, their touch screen is going to be likely based on silver nanowires instead of ITO, because ITO is kind of like inorganic system, could have cracks or that kind of things being formed during the touching process. And this system is going to be more robust. Also, performance-wise, I heard is also better. Okay, in terms of performance. Okay. So finally, let me show you another application we're exploring in collaboration with a few companies. This is about fuel cell catalyst. I know Minghua and other groups over here are also exploring along these directions. And proton exchange membrane fuel cells actually is supposed to be the cleanest source of energy, okay, for transportation and many, many other applications. In this device, basically just supply hydrogen and oxygen to different electrodes, and one is going to have oxidation reaction, one will have reduction reaction, have electrons being transferred out, and they generate electricity. And the products of this reaction is going to be water. The water is so pure you can even drink it, I'm sure. And then, of course, the electricity can be used to drive devices and so on and so forth. And Toyota actually started to commercialize this for passenger cars from last year. And I don't know about Hong Kong, actually in Japan and in US actually. They already start to form a reasonable market. And last year they sold about like 5,000 vehicles in the US. This is mainly limited by two things. One is the gas station. Okay, you cannot go to ordinary gas station to get hydrogen gas. You had to go to some specially designed built gas station for hydrogen. And also there's some issue about something I'm going to talk about is the cost. Okay, right now this vehicle costs about like $50,000. Okay, so you had to have some support from government to buy this. This is just the ordinary sedan. Okay, relatively small vehicles actually. Okay, and but there's some niche for this direction compared to like electric cars. As we know, an electric car is another option eventually for transportation. For electric cars, one of the major issues is the time it takes to charge. Okay, typically it's overnight. Sometimes it could be faster. Okay, depending on how much you want to invest on the batteries. And also the mileage is another issue. For Nissan and some other brands, you can only drive like 90 miles and then you have to charge again. And for this vehicle, you can it only takes 2 minutes actually to add all the hydrogen gas that can run like 400 miles. Okay, so it's a kind of convenience actually you can imagine. Okay, and now of course one of the issues as I mentioned is the cost, because for these devices to be useful, you have to add a catalyst to the surface. Otherwise, this reaction will be too slow. And you can only generate a very, very low current density. That won't be able to drive any device. Okay, so that's why you need to add a catalyst to speed up these reactions. In particular, for oxygen reduction reaction on the cathode, actually, you have to add a lot of catalysts. This catalyst actually contribute a lot to the cost of the device, of the fuel cell device, and also the vehicles, of course. So for platinum, actually right now the catalyst is mainly based on platinum actually, but platinum unfortunately is very expensive. and also very limited in terms of supply. Okay, this is because the abundance. All right, if you look at the platinum, is right over here. Is even lower than gold actually in terms of abundance in the Earth's crust. So that's why the cost is going to be high. And also, if you think about the supply, okay, that's could have another issue. First, it takes a lot of efforts to make a very small amount of platinum, like 10 tons of raw material, 5 months of processing, and just make 1 ounce of platinum. What's worse, if you take all the platinum we have ever mined, you melt them to make a cube. That cube is only this size. That's all the platinum we have mined so far in the world, actually. And that's how little it is. You can think about the volume. But of course, platinum is very heavy, okay? So volume is one thing, mass is another thing, all right? But anyway, so you would like to think about how you can find a better use for this very precious metal. So that's basically one of the driving force in our research, try to solve this problem. And for platinum, current use of platinum, you can see a majority goes to the catalytic converters. Every vehicle has to have a catalytic converters installed. And in this case, they are based on platinum, rhodium, and the palladium, those precious metals. And that took about like more than 50% of the market in year 2006. And that gave us very little room actually to develop new applications like fuel cells and so on and so forth. So now let's see how we can find a better use for this. So what's really important is really the mass activity. Okay, that means how much current you can draw over this per unit mass of the platinum. That will tell you how much catalyst you need to deposit on the cathode, or okay, in this case. So the mass activity is a product of two parameters. One is the specific activity, another is specific surface area. And so if you want to have maximum mass activity, you would like to maximize specific activity and specific surface area, these two parameters, right? And right now, for the commercial PTC catalyst, they have very tiny size. It's about like 3 nanometers. So that's why their specific surface area tend to be very high. It's about 60 meters per gram, or even higher actually, okay? However, for these very tiny particles, their specific activity tend to be very low because their size is so tiny. You are going to have a lot of atoms located at the corners, edges that tend to be not good for oxygen reduction reactions. And so that's why overall the mass activity is not going to be great. Actually, it's only about in this region shown over here. So now let's see if there's any way to maximize both of them. Okay, so let's see how we can increase the specific activity. Well, about like 6 or 7 years ago, we had a project with UTC Power when Minghua was there. We had some collaboration. Okay, but before I show you that result, let me show you some other things we should pay attention to. In terms of the surface structure, typically for most of the reactions, in particular oxygen reactions, they are going to be surface sensitive. Okay, you have to have specific structure in order to achieve the highest specific activity. And in this case, the 111 facet is going to be better than 100 facet. Okay. However, when you go down to very small size, this is the size of the particle, and the proportions of atoms at this specific size is going to be reduced because the atoms at the corners and edges are going to increase very significantly. So that's why for current commercial catalysts, their size is so small, you won't be able to optimize their specific activity. So that's why they tend to give us lousy specific activity. So we have to first increase their size, and then you can take advantage of the surface structure effect. So that's why typically, if you think about the surface engineering, you have to think about particles in the range 10 nanometers or larger, not in this small size range. Okay, so that's about size. And then about the composition, platinum turned to be the best. If you think about this volcano plot, this is basically the activity as a function of the bonding energy for the oxygen species on the surface. And this is a well-known phenomenon for catalysis. The binding cannot be too strong or too weak. So it has to be optimized somewhere in the middle. Okay, so that's why it's called a volcano process. Like platinum is sitting at the top over here. It's turned out to be the best. And for silver, palladium, they may have something close to platinum, but unfortunately, in particular palladium, for example, those metals actually are not so stable compared to platinum. They could be oxidized, for example. So that's why platinum stands out over there as the best choice for oxygen reduction. And composition is also important. You can form alloys, like shown over here. You can have PT nickel if you can mix them to form alloys. And you can see this specific activity could be increased very dramatically, actually. Okay, this is compared to platinum 111. This is PT nickel 111. Actually, could be increased by more than like almost like 15 or even 20 times that kind of range. So that's basically the results based on single crystal substrate measurements. So when we work with Minghua 6 years ago, 7 years ago, anyway, we managed to make some PT nickel alloyed octahedron actually, and Minghua did some tests actually. This kind of catalyst turned out to be quite remarkable, okay, as we would expect. So if you look at their specific activity compared to the PTC, actually, it's increased by almost like 50 times. And the mass activity could be increased by 17 times. So that means if you use this catalyst, the platinum loading could be reduced by 17 times, actually. Okay, so that's basically the simple mass calculation, okay. And we thought this system could solve the problem, but unfortunately we had some more study, and we also collaborated with GM after Minghua left. Okay, we did some tests. We found this system not so easy to put in commercial use because their durability actually turned out to be a problem, and their activity will drop very significantly because PT nickel is an alloy, and basically nickel is so reactive, will come out very easily. So that's why their durability, their activity will drop quite significantly over different cycles of test. And we also try to stabilize it by putting some platinum shells around it. There's some improvement, but overall, yeah, it may not be very ideal. So there are two options to make them stable. One of them is based on the intermetallic nanocrystal because those are alloys. Alloys tend to be less robust because the nickel could be easily leached out. If you make intermetallics, actually, that system could be supposed to be more stable. It's an ordered structure. Okay, so that could be one way actually, but now still impossible. Has been very challenging to make PT3 nickel intermetallic octahedron. So it's still challenging to accomplish that. So that's why we switched to a different system when we start to work with Toyota a few years ago, 2 years ago. So in this case, we come back to the pure platinum. Instead of thinking about alloying them to increase the specific activity, we just want to work with a pure platinum, but we are going to do surface engineering to make sure to have the highest specific activity for platinum, like 111 facet guarantee. And then also want to increase their specific surface area, okay, without sacrificing the durability. So here are some ideas. This is the PTC catalyst. I'll use very, very tiny particles, okay. So that's actually, I already mentioned, is not good for specific activity. At the same time, these tiny particles tend to aggregate during operation. Okay, so it's also making this durability worse. And nanoframe is one option. In that case, compared to this one, you have some advantage to maintain high specific surface area. This is like skyscrapers. This is like a small house. So you can use the vertical direction basically to increase the specific surface area. And they are already in this kind of frame structure. Suppose they are going to be heavier. Actually, it won't be able to sinter and move around and sinter so quickly. And there are some other options. You can make like something called a nano sheets. You only have a few atomic layers of platinum, but still it's very difficult to make them and use them. Typically they have to be stabilized by surfactants and so on and so forth. If you make them relatively large area, you won't be able to easily put them on support. Okay, so that's why we thought about this, but we didn't use that approach. And here is the approach we look at it. One is to make a core shell structure. So I already showed you how to make palladium-platinum core shell structures. So in that case, the shell could be controlled at maybe 2 atomic layers thick or 3 atomic layers thick. So basically, it can increase the dispersion of platinum atoms or utilizing efficiency of the platinum atoms. Or you can etch away the palladium eventually to make these hollow structures. We call these nanocage structures. And if you can control the wall as thin as like a few atomic layers, and we believe this can give us a good catalyst to use. And in the future, maybe they should become the choice for the catalyst. And if it's only 2 atomic layers, and both inner surface and outer surface can participate in the reaction, so essentially you don't waste any platinum atoms, so you are going to have the highest possible utilizing efficiency for atoms. And you can have a 1-1-1 facet on both sides. You can have a high specific activity. So combined together, looks like you can give us a platinum-based catalyst with high activity and good durability, because this structure could be made as big as 10s or even like 20s of nanometers. It doesn't matter, okay, because all the atoms essentially going to be located on the surface. So that's basically the idea. And here is the approach I already showed you earlier. You can make these core shell structures by starting with palladium and coated with platinum, only a few atomic layers, then etch away palladiums. And the key point over here, you have to make sure you can make a conformal coating. Otherwise, you're going to change the facet on the surface. And this is already very clear from previous discussion. You have to make sure diffusion is going to be able to overcome deposition rate so they can have a conformal deposition. Otherwise, they may form islands on the surface, right? So once we have made this core shell structure, you can etch away palladium. The reason is very simple. Whenever you deposit A metal on B, it's impossible. It's kind of naive if you think about like a pure A core and the B on the shell. They are always going to have interdiffusion and the mixing. So that's why always going to have some palladium mixed in the platinum shell. And then you can serve as a channel for etching, and eventually you can etch away the palladium and to obtain this pure, essentially pure platinum nanocages. Okay, in this case, this just show you TM images along this etching process, and finally you can make this almost like a 95% pure platinum nanocages. You might still have some palladium trapped in it, but it's very, very small number. And this is the octahedron shape. This is a cubic shape. This is octahedron shape. We also test their performance for ORI actually tend to be increased in terms of activity and durability. But here I want to show you another structure that's not even better than the octahedron. So that's based on the icosahedron. Icosahedron is related to octahedron because the surface is also 1-1-1. But at the same time, you're going to have some twin boundaries. You have 20 twin boundaries between these different facets. And these twin boundaries actually eventually will induce strains on the surface. And for ORI and other reactions, actually, these strains can have a way to further enhance their activity compared to 1-1-1 facet. So we can take palladium icosahedra, and you can coat their surface with platinum, and then you can etch away palladium to form icosahedron-shaped platinum nanocages. So here just show you the core shell structure. You have palladium core, you have platinum being deposited on the surface. There are about 3 atomic layers. And eventually, you can etch away the palladium to form this hollow and porous icosahedra platinum nanocages. You can also maintain those twin boundaries on the surface. And for the initial study, we found that you can observe pretty high specific activity. This is about 3.5. It's as high as the PT nickel alloy I showed you earlier. And the mass activity is a little bit lower than the PT nickel alloy because in the first demonstration, this shell was keeping about like 6 atomic layers instead of 3. That's something we would like to eventually reach. So that's why the mass activity is only 1.28. If you can reduce to 3 atomic layers, this could be increased to at least 2.0 or even higher. Okay, so that's definitely enough. So this system can also tend to be stable because the structure over here is about like 18 nanometer across. That's relatively big. Okay, so that's actually the current focus for us now. We have some collaboration with different companies try to really push this to the final ideal structure. Okay, icosahedral platinum nanocages with only 3 atomic layers thick for the wall. Okay, so that's basically what we are doing. This is the last slide. Basically, it's related to the application I just mentioned. And as we know, no matter what you do, you always have to think about scaling up. Okay, if you only make 10 milligram of your particle, it's good. You can publish a paper or 2 papers, that's for sure. But if you want to send samples to companies for some tests, you need grams at least, okay, even eventually you need kilograms and this kind of scale. And for scaling up, actually, people used to tend to think in this way, just use a larger container, use more reagents, and of course you're going to have more products. But unfortunately, it turned out to be not so easy because for nanocrystal synthesis, always involve heat generation, heat dissipation, and so on and so forth. And this is like a volume related thing. At the same time, generation of heat is volume related, but for surface, for heat dissipation is like surface related. So it's always not going to be a simple scaling up factor. So that's why I won't succeed. Okay, you won't be able to succeed if you go this way. Your particle definitely will be become less uniform, poorly defined if you go to a higher volume. So that's why we use a different approach. We are going to reduce the reaction volume for the synthesis to make small droplets. So you're going to have a continuous flow of these droplets, and the volume-wise could be even smaller than that. Okay, so if we take reagents and you carefully mix them and then disperse them into these droplets, and then you let them pass through this reaction zone, basically heat up using oil baths. And then you're going to have nanocrystals being formed in each individual droplet, and then you collect them all together. And in this way, you can easily make grams and kilograms of samples because this device could be running continuously, okay, without us being stopped. It could be also run in parallel. You can have multiple this kind of setup running at the same time. So this is also cool. Let me show you a movie. Okay, it's kind of like interesting to watch. So you can see the precursor being introduced. It's a yellowish color droplet. And then passing through this reaction zone, you can see they become kind of like black color. So that indicates formation of nanoparticles in each droplet. And this could be running continuously as long as you want. So of course we had to shut down. We don't want to waste too much of your precursors or reagents, right? Until you have requests from companies for these nanoparticles. So for example, for the palladium nanocube synthesis we run in this kind of droplets, you can see their quality is just as good as we can obtain from the batch reactors, and if not better, okay? So that's why we believe this is one of the future options if we really want to scale up this nanocrystal synthesis. So with that, I want to thank you again. I'll be more than happy to answer your question. That's the last slide. Thank you.
Okay, so I have a specific kind of problem that is the next layer on your nanocrystal, maybe. Mm-hmm. I have a very large protein complex, which is unlikely to be able to be crystallized directly. It's a number of different subunits all together, probably on a DNA fiber. And it's the way we would expect to be able to look at it right now is by cryo-EM. But crystal would be better. So it strikes me that maybe, although I know temperature is a problem, it might be possible to layer a
crystallization, all this
onto your nanoparticle.
Yeah, it's always, definitely temperature is one of the most important parameters to look at, both for crystallization process and also coating process. Yeah.
So maybe we could think about it.
I think so. But for biologic system, there's limited range of temperatures to use, I guess.
Although I do have the complex cross-linked with formaldehyde.
Oh, so I see. That might be, stable.
Might help.
Yeah.
But I have enough of the material we could play with it, and I can make a lot more. And layering it onto a pre-existing ordered seed might be a way to get started, because getting the initial seed to form in crystallization of very large protein.
Exactly. Yeah.
Okay, so we can talk.
Yeah,
later.
sure, definitely. Yeah, that's a really interesting direction actually to move into softer material or other, systems. Yeah.
Okay, any other questions?
Hello, Professor Xia. I have a question about that platinum nanocages. As you said, because platinum is a very expensive rare metal, so you want to make this nanocages as a high-efficient catalyst. But I think to make these nanocages, first you need to use palladium to make a cost. And then, did you just throw this palladium away?
Right now, of course, we do. But in the future, when you do manufacturing on large scale, you want to recycle this palladium. And also, I can tell you, you can also use silver. You don't have to use palladium. Palladium is just something we started first. Yeah.
What I want to ask is that, did you try some much cheap metals like iron?
Like silver. Silver, you can do it. Iron might be a challenge because they have different crystal structure. But you might be able to make even more reactive catalyst, who knows? Because iron is a BCC structure. So you can make a BCC platinum that could be something, interesting. I don't know, what you can think about. But it will be challenging to deposit the platinum on iron. Iron is so reactive. You're going to have galvanic. You have to find ways to suppress the galvanic reaction. Then you can do deposition.
Thank you.
You talk about the commercialization of silver nanowires.
Yes.
But of course, as you know, many people produce silver nanowires.
We are the first.
C3 nano is another
I just want to point out that.
So I would like to know if you compare your silver nanowires to, for example, Professor Baus from Stanford, she also.
They follow our protocol, I can tell you,
so
to make the silver wires.
So
I'm not talking about the
that's okay.
device, those kind of things. I really didn't do any exploration along that direction, but we invent that material. That's the thing. Yeah.
I want to know, but that's my question. How do you compare? Because at the end of the day,
they compare. The companies compare, of course.
No, the product. How do they compare in terms of the quality? In terms.
So that's why it took so many years to commercialize. They licensed our technology in year 2004, I believe. And it took almost like 10 years for this company to really finally figure out all these details, because you have to make sure your display is same quality as ITO based, even better quality, and you make sure the lifetime is long enough. They can operate under different humidities, different temperatures. So that's why they spend millions, hundreds of millions of dollars actually on that.
No, that is the second half. But the first half may be, for example, aspect ratio, about the way it is produced.
We didn't do any research in that regard. Okay, I just want to make that clear again. Okay. We just invented the silver nanowires. All the applications were explored by companies.
Okay.
And
I got you.
Yeah.
May I have another one?
Sure.
Now, there are many papers on making nanoparticles.
Yes.
And in the first half of our talk, you mentioned all the techniques and so on. But I always wonder, how can we generalize all these techniques for different materials, for different...
that's a very good point. Okay, very good point. I do have slides here. I gave a talk at the Hong Kong U actually the other day. That was in chemistry department, so it's like more. So there is one way eventually to have a universal way to control the nanocrystal synthesis. That's the kinetics. If you have the right kinetics, you can get the right single crystal seed or multiple twins, whatever. And then for the growth, you also have kinetics. So kinetics is the key actually. Not to be.
Well, but
it doesn't matter what kind of matter you are dealing with. Is the reduction kinetics actually.
So, but you also have capping agent. You still have other.
It doesn't matter anymore under that kinetic argument, because capping agent also just changed the kinetics.
But that depends on the database. So I wonder when do you think if it is at all possible?
It is possible.
Have the database, the knowledge base, to combine them in such
a
way that we
yeah.
can do it for different shapes and different systems. I just wonder what you think.
Yeah, so basically that's our most recent studies. We figure out the reduction kinetics is the key to control everything. For example, like what kind of seed is formed over here? A single crystal ones, singular twinned, multiple twinned, is the initial reduction rate. We have evidence to show you have reduction rate above certain level, they are going to make this one. And then you reduce the reduction rate to certain range, you make this one, and then so on and so forth. It's the initial reduction rate. We have evidence. We also observe that in a number of systems. So really it has nothing to do with silver or palladium anymore. Of course, for different systems, the reduction rate for specific structure will be in different range.
So in your talk, you talk about copper, but what other metals have you tried?
Oh, we tried copper is over here. We also tried silver, gold, palladium, platinum, all these guys.
Okay.
Yeah. Yeah.
All right. Okay. Thank you.
Mm-hmm.
The nanoparticle, they have a lot of surface areas. So can you comment on the stabilities, like shell life? That's one. Second is that the shape control or directionality control, they are also like Sun and others try these using electrochemical depositions, which you can control the deposition rate versus diffusion rate. So can you comment on these two approaches?
Okay. So first about the stability, of course, if you put this on support, it's okay. No, it's not an issue, right? And this particle will maintain, stay as this, separated or whatever, configuration. In the solution, of course, you have to have surfactants or polymers, those things on the surface. Otherwise, they are not going to be stable. Okay, so that's, of course, there's something you have to deal with by adding stabilizers always. And your second question about the electrochemical deposition, that's similar. Electrochemical deposition, after all, is just another way to reduce salt into atoms. It should be supposed to be the same if you're using chemical reduction. It's essentially similar. But electrochemical reduction has another advantage, of course. You can more precisely control the rate than chemical reduction. You can change the current density and or those maybe pores. You can control exactly the rate.
More on the mass production side.
For electrochemical, it's not going to be easy to think about the larger scale. But of course, electroplating, it can be operated on very large scale. But for this kind of dedicated synthesis, I don't know if we can do it or not. Okay, yeah. But it could be a way to make them well suited for large scale production. That's feasible, yeah.
Okay, so thank you very much.
All right, thank you.
For these very exciting talks.